Okay, let's get started on this Unit 2 practice test. State Newton's laws. So we got Newton's law. We put them in order, first, second, third. The simplest word would be inertia. Sounds like Bill Nye, property of inertia. Basically, things will keep doing what they're doing unless there's an unbalanced force. And it says, give an example in the world. Kick your foot against the wall and all the snow comes off because the snow wants to keep going, but your foot stops. The second one's a proportionality between force, mass, and acceleration. Because Newton picked 1 Newton to accelerate 1 kilogram at 1 meter per second squared, it's just a perfect equation, F equals ma. An example in the world would be, I can make a race car go faster or accelerate faster if I have more force in the engine, or make the race car lighter. So it's directly proportional to force and inversely proportional to mass. And the last one, third law, is reaction forces. Well, some people say action-reaction forces. That's where all the forces occur in pairs on 2 different objects. So examples in the real world would be like shooting a shotgun. The bullet gets pushed forward and the gun pushes back on you. Or a cannon, anything like that, or jet propulsion. Okay, so you can look them ones up. That's easy. We'll stick to the math ones here. So there's a go-kart with a mass of 120 kilograms. There's a thrust of 1,400 newtons. There's no mention of friction or anything. So that's probably your net force. F equals ma. So we got 14,000 newtons equals 120 times the acceleration. A equals 1,400 divided by 120. 11.7. Okay. It says draw a free body diagram of a 30 kilogram box. Push with a forward force so that the box is accelerating at 2 meters per second squared, which means it's going to have a net force. Here's the box, 30 kilograms. You can always put in gravity because it's always there. 294 newtons. The box is not going up and down, so our normal force will also be 294 newtons. Somebody's pushing forward on the box, and we have friction backwards, 60 newtons. And the box is accelerating in the forward direction, so whoever's pushing on the box is pushing with more than 60. We know that F equals ma, so it's a 30 kilogram box, acceleration of 2, that's 60 newtons of force, net force. So that means when I push forward, I subtract friction from what am I doing, and the leftover has to be 60. So this guy would have to be 120 newtons. Because 120 minus 60 will give you a net force of 60, which creates the acceleration of 2. Okay, let's go to the next page. Student slides a 45 kilogram box across the floor at school. The coefficient of frictions are 0.8 and 0.43. How much to get the box moving? So that means up until the point where it goes, it's sitting still. So we're going to use, this will be a mu s question. There's your box. You can put those 2 in because it's 45 times 9.8. We got 441 newtons, and this will also be 441 newtons, and friction's based on the normal force. And they're saying just to get it to move, so you're going to be pushing forward with exactly the same force as friction, just to the breaking point. So I need to figure out friction here. Force of friction equals mu s times Fn. We have all these numbers. It's 0.8. The normal force was 441. And comes out to be 352.8 newtons. And this is how much to keep the box moving. So that's mu k. You're not accelerating, you're going at steady speed, so all the forces are going to balance, just like this case here. So it's the same box, same force of gravity, same normal force. Okay, and then we have some forward force, and we have friction, and they're going to balance each other out, so it just keeps going steady at the same speed. Just like if I was pushing my calculator, I just keep it going steady. I still need to push on it, but just enough to overcome friction. Okay, so we got mu k, it's 0.43. The normal force is still 441. So there we go, 0.43, 41, and that gives me 189.6. And you've done this before. If you're trying to push a big box on the floor, you push really, really hard. Once you reach that point, the box starts to go, and then you can ease off on your pushing to maintain the velocity. Okay, let's start the inquiry part here though. So we got a cable with an elevator, and there's tension on the cable lifting it up, and it weighs 1,200 kilograms. So we can figure out gravity right away. 1,200 times 9.8, that's 11, 760 newtons. It's being held steady. Okay, it means it's not going up or down. It's just being held there, which means this will be the same number. So my tension will be 11760 newtons. The cable can actually hold 13,000. This is only 11,000, so the cable's not going to break. The next step, they said, okay, we're going to turn on the motor and we're going to start accelerating the elevator upward at its maximum tension. So the same box again, 1,200. This guy's still there. Gravity never goes away, but we're going to crank up the tension to the full strength. Okay, this guy's definitely winning. So if I did F net, it's a tug of war. 1,300 in the up direction minus the down direction. That's going to give me 1,240 newtons in the up direction, which is your net force. It's going to be pushed upward at that speed. And then you can only use F equals ma with the net force. So we have the net force now. And it's 1,200 kilograms. It's 1.03. Okay, that would be the acceleration of the elevator. Oh, I don't want to lose a mark. It's a vector. You have to tell me which way it's going. Is that elevator going up or down? It's up. Okay. All right, got my 400 kilogram satellite in my backyard. What's the force of gravity? Well, that's just Fg equals mg. 400 kilograms times 9.8. So 400 times 9.8 is 3,920 newtons. That's the force of gravity. What if I took it up in space? Well, here's the Earth. There's a radius of 6,400 kilometers. This guy, divided by 6,400, let's see, 32,000. That's 5 times Earth's radius. Okay, so you're quite a ways up in space. This is one radius. You're going to be 1, 2, 3, 4, 5 radiuses in space, which means you're going to be 6 radiuses out further. And gravity drops by the distance squared. So if you're 6 times further out, my new force of gravity here will be 3920 divided by 6 squared. 3920 divided by 6 squared comes out to 108.9. And that would be the force of gravity up this far. 32,000 kilometers above the surface of the Earth. That's the trick. All right, next one. Here's Newton's third law. Where a 36-gram slug leaves the end of the barrel, 0.9 long barrel at 250. So the initial speed of the bullet, V1 equals 0. In such a short distance, for only 0.9 meters, that guy is going 250 meters per second. That's a fast acceleration. Okay, so let's find the acceleration of the slug. Okay, you can do a couple things. You can find the average velocity, 0, that's 125. Find the time inside there, divide the time into the velocity change, and you got the acceleration. Or we could use the combo formula here. 2a 0.9 v2 squared minus 0. Okay, let's solve for a. So 250, square that, divide by 2, divide by 0.9, and we got 34,722 meters per second squared. Yeah, that's pretty fast. If I divide that by 9.8, that's 3,500 times stronger than the force of gravity. Okay, what would the force be on the slug? Well, F equals ma. The slug is 36 grams, which is 0.036 kilograms, times that acceleration. got the acceleration on the screen, 0.036. Okay, it comes out to 1,250 newtons. That's on the bullet. Oh, I'm seriously forgetting something here. The bullet is heading west, so the acceleration of the bullet is west. The force on the bullet is west. And Omar, it's a student from last year. He weighs 86 kilograms, including the gun. He's going to feel the force on him will be 12,500 newtons to the east, and that's going to accelerate him. They want to find acceleration. F equals ma. 1250 equals his mass times the acceleration. Solve for a. It's already on the screen. Divide by 86. It's 14. And it's an acceleration. It's a vector. Let's not lose an easy mark. So it's 14.5 meters per second squared to the east. That's his kick from the gun. Oh, one more page to go. Free body diagram of this block. That's a big tug of war going on. We got 60 newtons to the east, 48 newtons to the west, 22 newtons south, and 13 north. That's your free body diagram. You could put the mass inside, 5 kilograms. It's being pulled in all different directions. Some of them you can cancel out quite quickly. I got 60 to the right, minus the 48 gives me 12. 13 up and 22 down gives me 9 down. Those are the intermediate forces. They're the components of a vector. We just got to put them back together again because it says add the vectors and draw the resulting force. So we just got to draw this guy. Over 12, down 9, and that will be my result there. And then we need that angle. So that force will equal 9 squared, 12 squared, add them up, square root them, it's 15. And the direction is mostly east with some south. So 9 divided by 12, inverse tan, 37 degrees. That's the force. And this is the acceleration. Well, F equals ma. That only works if that's the net force. Well, that's what we just figured out, so we'll be good. 15 equals 5 times the acceleration. A equals 3 meters per second squared. Don't forget your direction. And you're done. Okay. Last question. It's one of these component questions. Shruti is pulling Grace in her new wagon. She determines the coefficient of kinetic friction to be 0.15. She pulls up on the handle with a force of 140 newtons and an angle of 25 degrees. Determine the components. Okay, so here's the upward force. She's pulling with 140 and an angle of 25 degrees. Okay, let's find them. So X is cos, 25 cos times 140, 126.88. I'll just do 9. Put equals there. They're not negatives. 25 sine times 140 is 59.17 newtons. Okay. Now it says draw a free body diagram to determine the normal force. So here's the box, 68 kilograms. Might as well throw gravity in right away because it's always there. It's 666.4. And we have a forward force, 126.9 newtons. We got a normal force up, and we also got the person pulling on it. And we're going to find out some friction later on, but that's the next part. I need to find out what's the value of the normal force so that this guy is not going up or down into the ground. So we know that there's a tug of war going on. Okay, the two up forces have to fight the down force. So the normal force will not be gravity this time because somebody's lifting on this go-kart or this toboggan. So we got a normal force of 607.26 newtons. And that's what that question says. And then it says determine the force of friction. It's sliding, so we're going to do mu k. They gave us 0.15. we'll just keep going across with the equal sign. 91.1 newtons. That's my frictional force. And now we gotta find the acceleration, so we need to find the net force, but up and down canceled, we made sure of that. So the only thing here is there's a tug of war between the forward force minus our friction force. And we get 35.8. That's the net force. Once you get the net force, now you can do F equals ma. So 35.8 equals 68 times acceleration. A will equal 0.53 meters per second squared. And that's it.